The next thing I want to talk about are limits of infinite sequences. And so when we talk about convergence, and we're going to talk about this word a lot in the notes today, when we talk about convergence, what we mean is that the sequence of numbers settles down and eventually starts approaching a certain number. And that number is called the limit of the sequence. And so if a sequence of numbers eventually settles down and approaches a value, a specific non-infinite value, then we say that the sequence converges, and it converges to whatever that number that it's settling down to. And so I hope that makes a little bit of sense. Hopefully through the examples it'll make a little bit more sense. And so let's look at this first example. We have the sequence 1, 1/2, 1/3, 1/4. You can probably guess what the next term would be. 1/5, 1/6, 1/7, 1/8, on and on and on. This is an infinite sequence, as you can see by the ... at the end. And so eventually that denominator is going to get so large that you're going to have terms that look like 1 over a million, and then 1 over a billion, and 1 over a trillion. And think about how big that is. It's not very big at all, because 1/1 trillionth is very, very tiny. And then you're just going to keep going past trillion into whatever the next name of the number would be. I don't even know. But eventually that denominator is going to get so large that the fraction itself is basically 0. And it's never going to actually equal 0. So that's what you have to be careful with convergence, is that we're not saying that the sequence will eventually equal to 0. We're saying that it will converge to 0, meaning it will approach 0 and get as close to 0 as we could possibly want. And so what we're going to say here for number 1 is that this sequence of numbers converges because the limit, as the number of terms goes to infinity, of that particular formula, 1 over n, is equal to 0. And so we can say here more specifically that this sequence converges to the limit of 0. So hopefully that's making a little bit of sense. I'm going to do letter B here, which is somewhat similar. The only difference is that we don't have a nice formula like we did in number 1. Here we're going to have to actually create our own formula, which is not always possible, but it is going to be possible in this particular scenario. So I want you to look here with me at the first term, 2, which could really be written as 2 over 1. And so if you look at those denominators, it looks like they correspond to the term number. So for example, the first term, 2 over 1, has a denominator of 1. The second term has a denominator of 2. The third term has a denominator of 3. And so how do we represent the term number? Well, we use the letter n. And so the denominator is n. And now look at the numerator of all of those fractions. What is the numerator with respect to the denominator? It is 1 more than the denominator. Would you agree? And so therefore the formula for this sequence would be n plus 1 over n. And so what I'm going to do first is I'm actually going to try to find that particular limit as n goes to infinity of n plus 1 over n. And now, this is the beautiful thing. You relate this back to something that we talked about back in chapter 1 and again in chapter 2, which is that if you have a limit at infinity, you are essentially finding the horizontal asymptote. And we know how to find the horizontal asymptote of this rational function using Bobo-Botten eats DC. And so this particular function, the exponents are the same, therefore we're going to divide the coefficients, and we end up with a limit that is equal to 1. And so because that limit is finite, meaning it is not infinity, we say that this sequence converges. And more specifically, we can say that the sequence converges to 1. Okay, letter C we see is an infinite sequence that has a pattern, 2, 4, 6, 8, 10, 12, 14, 16, on and on and on and on and on. And so you could probably find the formula to this pretty easily. It would just be 2 times the term number. And so is this going to converge, meaning it will eventually settle down on one exact specific value, or are the terms going to either increase or decrease without bound, or bounce back and forth between 2 or 3 different numbers? And hopefully you can see that this sequence is going to increase without bound, and so whenever a sequence increases without bound, we say that the sequence diverges. And so there's no need to find a limit because the limit of this sequence does not exist, and that's true for any sequence that we call divergent. And so for letter D, this is a special kind of sequence, and we mentioned it in passing a little bit earlier. This is what is called an oscillating sequence. And it's oscillating because it is bouncing back and forth between 2 values, -1, 1, -1, 1, -1, 1. It can't decide which number it wants to be. By the way, this is a little bit of a typo. It should be an infinite sequence there. And so there is no limit here because the sequence does not settle down on exactly one number. And so for that reason, and that reason alone, we say that this sequence diverges. Okay, now it's also possible to find the limit and determine convergence or divergence if this sequence does not have a pattern, but you know the formula. And the reason for that is because to find the limit, we're just going to take the limit as n goes to infinity of the formula. And so we know, based on what we said earlier in the notes and what we learned in Chapter 1 and Chapter 2, that to find this limit basically is the same as finding the horizontal asymptote. And so using our acronym Bobo-Botten Eats DC, this would fall into the Eats DC category, which would give me a limit of 3. And so because that limit is finite, meaning not infinite, we are going to say that this sequence converges, and more specifically, it converges to 3. Okay, letter F, again, same thing. We're going to take the limit as n goes to infinity, this time n cubed plus 2 over n squared plus n. And I see here that the exponent is bigger on top, and therefore this limit is going to equal to infinity because there would not be a horizontal asymptote. It would fall into the Botten category. And whenever that limit is infinite, we say that the sequence diverges. Okay, and then finally letter G, same thing one more time. We're going to take the limit as n goes to infinity of this particular formula here. And so you're asking yourself, where is the larger degree? And you see that the exponent is bigger on the bottom. And so that means that this limit is going to equal to 0. And that means that we can say that the sequence converges. And more specifically, we can say that it converges to 0.